welcome. We are going to discuss the recent high altitude balloon mission that we conducted on May 18th. On board were 10 CubeSats from teachers from all around the country, really. Majority of them were from New Mexico teachers. Some of them were from teachers who were participating with the Rural Technology Fund, so they come from a few different states. We do have a number of other CubeSats that from New York teachers that partook in our training last summer that have not flown yet. We're going to schedule another flight in the next couple of weeks to fly those ones. Turned out that we got so many CubeSats that it would have been too heavy of a payload to be able to fly on a single balloon. So we needed to split it up. And it's, as you all know from all of the emails that you got from me, it's been very difficult to schedule these flights due to difficult weather. This spring in the Northeast has been extremely stormy and windy and crazy temperatures. The jet stream has been abnormally far south, which has messed with the weather as well as winds. So it was hard enough just to get one scheduled. So ideally, the weather is much more temperate now. So we'll be able to get one done either next week or the week after, if not by the end of June. So here are all the CubeSats right here behind me. These ones in the front are the ones that we flew. I'm going to share my screen and go through some of the materials that are available. To begin with, on our website, you can find the video and the data from the flight. If you go here to the resources dropdown, you go to flight data. It's on tis.org. It'll bring you to this page, and it's in chronological order. So the very top one has the video as well as the data. And I'll go into that in just a moment. But first, I want to kind of go over some of the details of the flight itself. These slides are included in the video. If you watch that, like the first minute or two includes these slides. So we launched from a town called Oriskany Falls in Oneida County, New York, which is about an hour west of, maybe a little bit more than an hour west of Albany, the capital. Want to thank the New Mexico Space Grant Consortium for helping to sponsor all of this, the trainings, as well as the flights, as well as the amateur radio digital communications. They have been supporting us, and they have helped us to make all of this happen, as well as Change Happens Foundation and the Glenn W. Bailey Foundation. Thank you very much. So generally, we try to launch the flights as early as possible because surface winds are definitely can be an issue. You know, if it's really windy at the surface and you're trying to inflate a balloon and get a hold of it and not have it go flying into trees and whatnot, you want it to be a pretty calm day. And the later in the day you go, the more time the sun has to heat the surface of the earth, which causes updrafts and winds and whatnot. So we try to get it done earlier in the morning. This time around, we had some high school students come help us. So we had to wait for them to get to school before we could then drive about an hour to even get to the launch area. So we got a little bit of a later start than we would have preferred. Some of you who have been to our in-person trainings, you know that we usually will try to get to the launch location at like 5, 6 in the morning. That way we can have the balloon up, by 7 or 8 a.m. before there's time for that heating to occur and to create lots of winds at the surface. But regardless, it turned out to be a wonderful morning, and we found a location that was it was a baseball field actually, and there was not a lot of wind, so we didn't really have any problems. The balloon was able to get up to a maximum altitude of 96,543 feet, according to the onboard radio tracker. Now, those trackers send out a signal like once, I think it's like once a minute. So it could have actually gotten higher than that, but the highest recorded altitude was 96,000 feet. So give or take 100 or a few hundred feet. Not the highest we've ever gotten. It's not our record, but it is in the zone of, a great flight. If we can get above 80,000 feet, that's awesome. So we definitely passed that. The highest we've ever done, I think, was a New Mexico flight. I think last summer's Las Cruces training, we were able to get up to 109,000 feet, which is our record currently. The balloon came down at about 12:34 p.m. Again, give or take a minute or two. And also, you have to keep in mind that in order for the tracker to, send out its data and for that data to be collected, it has to be within line of sight of a repeater tower. And there's these repeater towers are all over the country. And while it's up in the air, it's actually being picked up by multiple repeater towers. But as it gets lower to the ground, as it's coming down on the parachute, it starts losing line of sight with those towers. Eventually, it gets to the point where it's low enough to the ground where it has line of sight with none of the towers. It's still technically in the air. It might be like 1,000 feet off the ground. It's dependent on the terrain around it. Like if there's a lot of hills and mountains, it can lose contact with those towers, before it gets to the ground. So ballpark 12:34 p.m. If you actually look at the website, the aprs.fi that I sent the link to, that everybody was able to track the mission, you'll see that like the last reading, I think it was like around 3,000 feet was its last recorded altitude. Sorry if you hear my dog barking. He tends to do that. So on board this flight, we had a 1,200-gram balloon, which is generally what we use. You could use bigger, you could use smaller. This is like really the sweet spot. When purchasing helium, which is what we use as our lifting gas, we generally will get a K tank, which is like one of those. They're about like 5 feet tall. They're those like big green metal tanks, and one of those can fill a 1,200-gram balloon, generally to the exact right amount. If you get a bigger balloon, you would need more helium and you need to use more than one of those tanks. And these days, helium is becoming an issue. Number one, it's not a renewable resource. It turns out that 30% of all of the helium in the world transits the Strait of Hormuz. So that's not very good right now. So helium prices are going way up, and just availability is going down. And it turns out that helium is very important for a number of very important types of processes, like manufacturing of semiconductors and computer chips, as well as cooling of imaging machines like MRIs. And so those uses generally are higher up on the priority list for getting helium. So being able to use the least amount of helium that you can for this application is ideal, just because it's getting more expensive, and we might get to a point where we just can't get it. There are other options. Some people will use hydrogen. We are a little iffy about hydrogen just because, it's a highly flammable gas. And the first thing that goes through my mind is the Hindenburg. And so like, especially when we're working with students and teachers, like we don't want any, danger involved in the process. So we're not really too keen on using hydrogen. We may have to eventually. I've also seen that methane is used, but again, methane is flammable as well. So, it might be easier to get your hands on. It may be cheaper, but it's not any safer. So we'll continue using helium while we can, and if we have to make a change, we will cross that bridge when we get there. So the balloon is what makes the payload go up, and the parachute is what helps the payload come down. Honestly, gravity will do that for us, but we want to not leave a smoking crater in the ground where our payload lands. So we make sure to use a parachute. We will generally use a 1.5 meter parachute. You can use bigger, you can use smaller, but it's important to know what parachute you're using, and it's part of the whole calculation to determine like what your descent rate is going to be, because that goes into the planning of the flight so that you know approximately where it's going to land. Then on board, we had a StratoTrack APRS tracker, which is what was communicating with APRS.FI, which is how you were all able to watch in real time. And then we also put a spot tracker on board as well, just as a backup, because we have had in the past where something happens with the APRS tracker where it just stops communicating, and it's just good to have that redundancy. In this case, we didn't need it. The APRS tracker worked perfectly, and we were able to find it with that. We didn't even have to look at the spot tracker. And then on board is an Insta360 1X camera. It is a 360-degree camera. It's got two lenses, one on each side of the camera, and it automatically stitches the two views together. And then I have the option in the software that it comes with to then edit the video so that you see what you have seen in the videos that I've posted from these types of flights. And then we had 10 CubeSats, 10 1U CubeSats on board with temperature, pressure, accelerometer, gyroscope, real-time clock, light sensors, various types of light sensors. We had at least one of the CubeSats had infrared light sensor on there as well. And then for the camera, because those action cams, as they're often called, those 360-degree cameras, like a lot of people use them for like extreme sports, whether it's like mountain biking or dirt bike riding or whatever it may be. The onboard batteries on those generally don't last very long, like maybe like 30 minutes, and then you have to switch out the battery. And it's nice that you have the option to, switch the batteries out. But unfortunately at, 60,000 feet and up, there is no option to switch out the battery. So what we have done is gotten like these external USB batteries that you would use, to like top up your phone or whatnot. And what you can do is you can actually take the battery out of this particular camera. I don't know if you can do this with other ones, but I found that you can take the internal battery out of it and then just hook it up to one of these battery packs with a USB cable and run it directly off of this. And this is way bigger. This is 5,000 milliamp hours. I think the ones on board, well, I've got battery. So you can see the difference in battery size, right? This is a 1,050 milliamp battery. So this is almost 5 times more battery power. And this one will last, it depends on the temperature, but generally I've always been able to get the full flight out of one of these. And the flights are generally anywhere from like an hour and a half to 2 hours long. And then we also had a number of seeds on board. So at least one of the CubeSats had the seeds directly built into the CubeSat. So this one right here. And then a couple of other schools sent their seeds in like packets that I taped on the inside of the box that was holding the CubeSats. So there were a number of experiments that wanted to see if sending seeds up to the edge of the atmosphere would have any impact on their germination rates and whatnot. So here is a shot of the CubeSats. You can see down here, here are 2 of the seed packets. And then these are our CubeSats. So this right here is the, this is what we used to do the actual planning, right? And if you watch the video that I put out last year about the high altitude balloon mission planning, and that's available on our YouTube page, you could see all the details that go into making this prediction. So the way that we do it is we get an idea of where we want it to land. And so we wanted it to land over here near Canajoharie because we knew that this was like a very farmy area, a lot of wide open fields, not a ton of trees, not really very many mountains. So we felt safe that it would land there. And then we worked kind of backwards from there. So you have to plug in, your variables, like what is the ascent rate, which was going to be 5 meters per second. What is your, and in order to find that, we use a different calculator where you plug in like what is the weight of your payload, what size balloon are you going to use, and then with that you can get the ascent rate, and then you also plug in your date and your time, and then your descent rate, which is based on your weight of your payload and your parachute, and then that'll be able to then calculate where the approximate landing location will be. So with all of those things plugged in, we were able to then, over the course, it took us like maybe like a half an hour of like guessing and checking. What we would do is we would click on a potential launch zone, and that's important. Like, we can't just launch from anywhere. It has to be a pretty wide open area. It has to be accessible. And so we generally look for like parks, right? Public parks are great because they're usually wide open areas. They're accessible. Anybody can go there. And so we looked. We knew that it was going to be traveling to the east. So we went to the west and we just started looking on Google Maps for various parks. And we actually found like 3 or 4 of them. And so then we chose those as our starting locations. And we looked to see if the landing location would be in this general area here. And we wound up choosing one of those parks, which happened to be in Oriskany Falls, which it was a baseball field. And so this is what the planned route was going to be, right? This is what the flight plan was expected to be. And then this is what it actually was. So the biggest landmark on here is this Otsego Lake, or Otsego Lake. I'm not really sure how you pronounce that, just north of Cooperstown. So you could see originally we were planning on the whole flight being pretty much to the north of that, and then the landing to be to the northeast. But it turns out that the amount of helium that we had in the tank was actually a little bit less than we were expecting. And so we used that entire tank to the very last drop, and we still were expecting to get a little bit more out of it. And so because there was a little bit less helium than we had calculated for, it kind of changed. It shifted the flight path a bit. You can see it pretty much they resemble each other, right? The general shape of it remained the same, but the whole thing kind of got shifted further south, and that was because it took longer to rise. So the ascent rate was actually lower than 5 meters per second, and so for whatever the winds were doing that day, that caused the southern motion, which you can see like it was expected to go south, but it just went more south. It went like more. It continued to go south for longer. And I'll tell you what, it was right above this lake, and it burst. So it burst like right around here somewhere, and I was like, oh great. I was like, it's going to go into the lake, isn't it? Like, that'll just be our luck. I mean, I shouldn't have really worried about that, because like at 90,000 feet, when it bursts, it's still going to take a while to come down. But if something happened to the parachute, which something did actually wind up happening to the parachute, I'll talk about that in a minute. You never know. Like, it could come down much faster than you're expecting, and so I was just stressing because that's what I was doing, while chasing after this balloon. I was like, that would really stink if it fell in the lake. It didn't, but you know, that's always a possibility. A neat thing about the aprs.fi website is there is an option to download a Google Earth KML file. And what you can do is you take that file and you can open it up in Google Earth, the desktop version, and it'll create a three-dimensional view of your flight path. So you can see what I was talking about with the line of sight. So the first reading from the tracker actually didn't happen until it was pretty high in the sky already. Like I think it was, a few thousand feet at least before we got our first reading, because that's when it had first got line of sight with one of those trackers. And then you can see as it goes up and then it curved back, gets to the top, and then it burst and it comes down much faster than it goes up, especially this particular flight, right? Like I was saying, our ascent rate was much slower than we were expecting. So it kind of meandered its way up and then it came down pretty fast. This was also the heaviest payload we've ever flown. This was 10 CubeSats. The most we ever flew in the past was only 9. So this was because I used these in the video. Something to keep in mind at the end, towards the end of the video, it's coming down and you can see it's just about to land and then it just like cuts out. And that was because the way that these particular cameras work is they only record a 30-minute file and then they stop, they save the file, and then they start a new file and start recording again. And apparently that takes a few seconds to happen. And so when you go and watch the video, you'll see that just as it's about to land in a tree, it just stops. And that's because after that, the next file, it was already in the tree. And like, I figured it wasn't worth putting that in the video. So it was just coincidence that it happened to be landing right at the end of that 30-minute file. All right, so let's take a look at some of that stuff. Let's start with the video itself. It's not very big. There we go. Let's go through. So here's just, packing up the CubeSats. While I was doing that, Chris Murphy, he's our resident balloon master, and he's on our board of directors. He was working with some students from Gloversville High School where he teaches and getting the balloon ready. I actually had some help myself. As happens, you could see in the background there, in the background, there was a lady with her dog who was walking by and saw us and was like, "Hey, what are you guys doing?" And then also that third hand right there was actually a town employee he had come to mow the lawn of the field. And he was like, "Hey, what you guys doing?" And like, that always seems to happen. Like people see us and they're like, "Oh, what's going on over here? What's this big old green tank you got here? What are you guys doing?" Like, people in the past have like asked us if we were doing nefarious things like launching missiles and whatnot. And yeah, it definitely draws attention. And like once you explain what it is you're doing, people are always like, "That's the coolest thing I've ever heard," and they want to be involved somehow and help out even. So this was actually quite helpful to have them there. All right, let's skip ahead a bit. So here we are about to let loose. There we go. So you can see that baseball field. Some landmarks you can see in the video right over here. This like plume of smoke is actually a quarry. It's a big quarry right there. So I guess that's just dust from the quarry. This is the town of Oriskany Falls. You can see there's some farmland in the area. Now, if you were to compare this shot of the balloon here at this point, this is like, 2,000 feet above the ground, to the shot of the balloon once it's at the peak. Let's see if we could do that real quick. Oh, too far. So you see that little speck in the middle? That's the parachute. It's a very small part of the whole radius of the balloon. Where'd that shot go? You could see pretty clearly how much smaller the balloon is at ground level compared to once it's way up there. So here we are getting higher and higher. And so like when I'm editing these videos, I'm always trying to kind of balance, the views of what's below, what's out, to the sides and what's going on up above. Now, something cool happened in this video that I've never seen before, which I think we are about to see. Where is it? Okay, it's right around here. So with the quality setting currently, you can barely make it out, but that right there is a jet flying by. And the way that I realized that was while I was editing the video, I didn't have the camera focused in that direction. So again, the way that this all works is that technically right now you have a 360-degree view with the camera. But if you were to just show the whole 360 degrees, it would show up as like a circle on the flat screen. And it would be difficult to make out any details because you'd have 360 degrees bent around in a circle. And so what you do with the editing software is you choose where the camera is looking. So at that point, like right before that, I had the view doing like a 360 to look around. And then while I was doing that, I had the volume up and I heard the jet, approaching and going past. And I was like, oh, there must be a jet somewhere. So like I was scrolling around looking for the jet and I found it. And so what I was able to do is then to have the view shift to where the jet was and to follow it as it flew by right there. So that was pretty cool. Now, it's important to keep in mind that when we do the planning of this the night before, we have to call it. Well, we technically don't have to, but it's very much recommended that you issue what's called a NOTAM or a notice to airmen. And essentially, what we do is after we know generally where the landing zone is going to be and where we're going to launch from, we call up a hotline and we tell them, we're going to be sending up a balloon. It's going to go up to about 100,000 feet. It's going to be traveling, east, southeast, between this time and this time. And then they issue that notice, and any pilots that file a flight plan that's going to go through that area will get that message saying like, be on the lookout for an unmanned aerial vehicle or an unmanned balloon, so that they can know that this is potentially there. Now, the likelihood of them actually coming into contact with the balloon is like very minuscule, but it's good to let them know just in case. So yeah, so in these videos, there's usually some cool little thing like that. I know in one of the other videos you could see from Las Cruces is either last summer or the summer before, after the payload had landed, a coyote actually comes walking up to the camera and is like scoping it out. It's like, what is that thing? So usually if you spend enough time digging through the footage, you can find fun little things like that in there. This time it happened to be a jet. So you can see, the difference in the sky as the altitude increases. So this here is about, midway through the flight. It's a little bit of a hazy day. You can see that haze, the ring around the sun and whatnot. But eventually we get to a point where we break through that haze layer. And now you can see like the sky is like a dark blue. And then eventually, as we get up even higher, it gets even darker. And you'll see like the blackness of space. So down below, it's hard to see with this quality. But right here is that Lake Ostego, I think it's called. That's what I was worried about us falling into eventually. As the balloon bursts and we get closer to the Earth, you can see it better. So now we're pretty close to the top of the flight, and you can see it's pretty dark, right? You can, especially when there isn't the glare from the sun, you could see the blackness of space. There's so little atmosphere at this point that it doesn't filter, or the blue is not. You can't see the blue anymore. Yeah, so that's a much bigger balloon now. It can increase up to like 7 times, I think. So there's our burst. And so when we had the balloon, when we were setting up the balloon, because Chris is such a nice guy and he like makes me be in charge of everything, um, he actually asked when we were putting the line together, he's like, "Do you want to put a piece of line between the parachute and the balloon itself?" And I was thinking like, "Oh no, let's try to have as little weight as possible. So let's not do that." And he's like, "Okay." Um, Later, when we were after we retrieved the balloon, he said, "Yeah, we probably should have put a line in between there because sometimes when the balloon bursts, it can wrap around the parachute." And that's precisely what happened. So you can see right there in this mass of white right here, that's where the parachute is. And that could have turned out to be a very, very bad thing. When you have another line between the parachute and the balloon, it's less likely for all of those shreds of latex balloon to like wrap around the parachute itself. So, lesson learned, won't do that again. But luckily, uh, it didn't wrap up the parachute so much that it didn't work. So, we were able to have a functioning parachute, as you can see here now. For the most part, the parachute is starting to deploy. You would actually see that there's parts of balloon beneath the parachute. So normally, if we had that second line above the parachute, it would have burst. Most of the pieces would have kind of just blown away, and you would have had like a little bit left attached to the top, but you wouldn't have had anything below the parachute for sure. This is the first time I've ever seen that happen. So, always learning, always improving our techniques. So at this point, the parachute is not really doing very much because there's so little atmosphere. This is now, minutes later, actually quite a few minutes later, and now the parachute is doing something. So we're getting to that cloud layer there. We can see the parachute. There you go. So now the parachute's really doing something. But even here, you can kind of see that it does look like it's got some of that balloon, those balloon fragments might be attached to the parachute itself, which is not ideal, but didn't cause too many problems. So now in this shot, I think you could see the landing zone actually. So this pond, we landed just right before that pond, if that's the right one. Oh, wait, no, I think it's actually this pond down here. It only looks like a little speck right now, but you'll see as we get closer. So again, it could have landed in another. Yeah, all right. That's the pond right there that we landed next to. Like probably 30 feet from that pond, and it looks like the balloon was actually going in that direction. So if it had gone a further 30 feet, it probably would have landed in the water. And right here, directly below it, this is like a big swampy area. So like there was water here too. So we wound up landing like right here. And there's this clearing, a little bit of a clearing right here. And we happened to land like right in a tree at the edge of that clearing. So very lucky. So you can see the shadow of the parachute right there. And, it comes down and it lands. Like I said, it landed like right around here somewhere, one of these trees. But it could have kept on going and would have not have been great. Luckily, that pond was not very deep. So if it did happen to land in there, like probably could have waited out and gotten it. But that would not have been great for the camera and the CubeSats and whatnot. So we're glad that didn't happen. All right, let's take a look at some of the data now. So when you open up this, we've got multiple tabs here on the bottom. Each of these represents a different school and or teacher name. So if you had written your school on the CubeSat itself, I put the school name. If not, I just wrote the teacher's name on there. These first two were somewhat unique CubeSats. They had different types of sensors on there, so they're going to look a little bit different than everything else. The one from Martin had a gas resistance sensor as well as an LTR 329 sensor, which has both visible, infrared, and UV light sensors on board. So that could be some interesting data to compare to your light sensors, whatever you have on yours. Lucero had some gas sensors on there. So they had CO2, volatile organic compounds, and then I guess hydrogen on there. And maybe this is ethanol. Yeah, I think that's ethanol sensor, which that could lead to some interesting information. And then we have the rest of them were the typical CubeSat that we generally fly. So those will all have the same types of sensors, which is great because you can compare your data to those other CubeSats and see, what the differences are. So let's make a graph real quick. Let's take a look at what temperature was like during the flight. So I'll choose the two columns that I want to graph, and I always choose a time because we graph against time as our x-axis. And so you could just click on the heading column, and I'll choose the whole column. And then you hold down Control, and you click on whatever the thing you want to graph is. So in this case, I'm going to graph temperature. And so by holding down Control, it selects both of the columns. And then you click Insert, and then click Chart. Now, the first thing that you're going to see is going to look a little bit strange. So take a look at your chart type. This is a column. Well, we don't want a column. We want a line, right? Generally, with these types of graphs, we want line graphs. And then for whatever reason, it always defaults to putting both of the data points in the series or the y-axis. So for x-axis, we need to add an x-axis. So I'll click here and I'll click timestamp. And then I will remove the timestamp from the series. And there we go. That's what I was looking for. So there is the temperature. So we started, just under 40 degrees Celsius. And the temperature actually increased because this is probably from when I put it in the box. And so it was just sitting in the box for a little while I was getting the other CubeSats ready. And so because you have all those CubeSats in there and they've got electronics running and the sun was beating down, and also the box that I put them in, what I did was I cut down one of the sides to make like a window. And then I covered that with a piece of packing tape. And so that would allow light to get through, because a lot of the experiments specifically wanted to measure light intensity, whether it was UV or infrared or just visible light. So I wanted to make sure that we could get a good amount of light in there. So with that being said, the sun is beating down on it while we're getting ready. So the temperature was increasing for a while. And then probably right around here is when we actually let it go and it started going up and started getting the wind and whatnot. And then you can see it got colder and colder and colder to a point. And for a while, the temperature kind of stabilized for a while. There were some definite spikes, and then it got even colder. And I'm wondering if maybe this was after the burst and as it was falling, maybe it was getting colder because of the wind rushing past it, the air rushing past it until it got down to the ground where it warmed up quite a bit. So I'm gonna delete that so that you guys can't be deleted, huh? Let's do that then. So yeah, so go ahead and you'll be able to do this yourself. You may want to copy all of this to your own spreadsheet. I don't even know that you'll be able to edit it like that because of the way that it's shared. So what you'll have to do is you'll have to, copy and paste this into your own spreadsheet so that you can actually edit it. So yeah, so go ahead, show this to students, ask them to do what I just did, get them to make graphs and charts, get them to compare their graphs of their data to graphs of one of the other CubeSats data and do some comparing and contrasting. Things should be similar because they were all on the same flight. However, slight differences in how CubeSats were put together could potentially change things. Where they were positioned in the box could potentially change things. So get them to do some analysis, some data analysis, and see if they can find any differences. Have them hypothesize like I just did, right? I was just like coming up with, off the cuff observations about, what was going on during the flight. Have them do the same thing, or maybe ask them questions about that, like, oh, what do you think was happening when, this little blip in the graph was going on, or like why would the temperature stop going down for a while, but then all of a sudden it went down even further and then it went back up again, right? These are all the types of questions that we want your students to, start investigating. The whole thing about this process is that you go into it, or your students go into it with these preconceived notions, right? We asked you to have them write experimental proposals of what they wanted to, experiment on, and what data they wanted to collect, and come up with what they think was going to happen. And now it's time to see what actually happened and to think about why those things happened. So yeah, so that was the flight. It was a very successful flight. Um, Pretty much all of the CubeSats worked. Unfortunately, uh, two of them weren't working on the ground, so I didn't even put them in. And one of them, it was working on the ground, but then when I looked at the data today, it looks like something must have happened mid-flight, and it jostles around a good amount. You saw it spinning, and wires can come out or sensors can come loose. And unfortunately, if one sensor fails for whatever reason, whether it's the sensor coming loose or a wire coming loose, that can cause like a cascading effect where it stops all of the sensors from working. And so I think that might be what happened. Um, the data actually looked kind of weird, like it wasn't showing like the timestamp and whatnot on it. And so like that leads me to believe that, and I was looking at it before, and yeah, the power wire for the real time clock was gone. It must have come loose, and then I bet if I go look in the box that they were in, it's probably in there somewhere. So yeah, unfortunately, that is the case. That happens. That's flight for you, whether it's space flight or atmospheric flight. Things break, things don't go as planned. But luckily, we've got 9 CubeSats worth of data here. So even if your CubeSat didn't collect data, you still have plenty of other data to work with. All right, so with that, I'm going to field some questions. If anybody has any questions, feel free to ask me anything that you might have a question about, whether it's about the CubeSats, the build, the whole process, the flight, the data, whatever you want to know. And if you are drawing a blank right now and like tomorrow morning you wake up and you're like, oh, I should have asked Noah this. Like, feel free to shoot me an email or give me a call or send me a text message, and I'd be happy to, answer whatever questions you might have. This is also being recorded, so if you want to show this directly to your students or you want to rewatch it at any time, I should have this on our YouTube page and our website tomorrow. I'll send out an email with a direct link and everything. Any questions, comments, concerns? It looks like all of the AIs are gone.
No, I'll go ahead and share the video. Once you share it with me, I'll since I'm going to have a lot of the kids, and then the other sixth grade teachers will have some other kids that, well, everybody did it actually. All sixth graders worked on it. But I have some of the ones that were in the after school as well, and got to work on it a little bit more and see if they have any questions, and then I'll forward them to you. That's okay.
All right. Yeah, that's fine.
Well, I have a simple question. Is that okay if that video I can share with the school board and?
Oh yeah. Yes.
Okay.
Please do.
Division. Okay.
All right. If there are no other questions, then that is that. Thank you for coming, and I look forward to working with you further. Please ask me any questions throughout the summer that you might have. Into next school year, if you come up with any questions, I'm still here for you. And we have multiple training events happening this summer. We're going to be in Albuquerque in June. We'll be in Seattle in July and New York City in August. And you can find all of those details on our website and the in-person training page.